The advice that I can give to all of you is, make sure that you go for quiz. I post these things immediately, go through it, see if there's any speaking points, give me a holler if you, don't know. Remember these things occur, everybody that took the quiz today is above average, so you're over 80. Okay, so one of the questions was, the first question is this, so we'll just before we get started. Oh, and Richard, I got email from your so your confusion was, okay, I know the product rule for two things, but what about three? Well, two things is good enough because you can consider this two chunks, small chunk, big chunk. So the product rule says it's f prime of x times big chunk plus f of x times the derivative of big chunk. Right. That's just straight up product. And this one is a baby product. So now you just keep going. And I mentioned the problem has to be kind of a little bit of a learning experience. Now you multiply this through. This pattern. But what happens in general is you have any number of functions, then you just break it down this way. Everybody takes their turn getting their derivative. Right, that's essentially it. Everybody has your turn getting. Okay, today we're going to talk about what is the text 3A. What is sort of the opposite of an English language word implicit? Explicit, right? What you all are used to doing is explicit differentiation. Somebody walks up to you on the street, he gives you a function, y equals f of x, y equals e to the x, y equals sine x, y equals squared, and you take the derivative. Implicit differentiation is allows you to take derivatives of functions that maybe you can't write it down explicitly, but you know it appears as part of some equation, right? It's implicitly defined. Let me give you an example of an implicitly defined function that you all could see. This is a circle. What's the equation for this? X squared plus y squared is whatever the radius squared is. It's all taken here. This is a circle radius 5 center of yours. Right? Somebody explain to me why this is not a function. It doesn't pass the vertical line test, right? Because, for example, if I specify an x coordinate right here, given this picture, that's not enough information to tell you exactly what the point is. Could be up here. That's why it's not functioning, fails vertical line. Now, what happens if I ask you, what is the tangent line? And of course, as we saw last time, really finding the tangent line is easy. The hard part is finding the slope. So 3, 4 is about, say, here. How would you go about that if you had this on a? Oh, okay, but what are you gonna take the derivative of? What's the first thing that you might do? See, the problem is, doesn't function. You're used to y equal f of x. Can you solve this problem here? Sure, how about this? I agree. If I solve this equation for y, I agree, I can this. Which is, this is not a very good form to write it in, take its derivative, so let's do this. Now, okay, it's a chain rule problem. Then what's the first thing I come to? Right, blob to the 1/2 power. Derivative of that is 1/2 blob minus 1/2 power. Am I done? Right, which in this case is minus 2x, right? So if I write this in form that's easy to plug in, I actually get negative x over 45 minus x squared. 1. Now, if I want the slope of the tangent line at 3, 4, what do I do now? If I plug in 3 here, that's going to be minus 2. And that sort of makes sense if you look at the pictures. Everybody agree that it looks like the slope that's negative. But what if I had this? Remember, that's kind of mirroring. What's that? Well, maybe for this function, actually it turns out that way, but my whole thing is shot in a certain sense because this is not a function, but this is a function. But when I made this choice right here, notice this equation is speaking to me. Voices again, and what it's saying is your y coordinate must be positive because you're taking the positive square root. So when you made this solution, you solved for this, and you took the positive square root, you're saying, hey, you know what? Forget the lower circle. This is what I'm thinking of right here. Just, I basically, this has the full information of the circle. This chops it in half. I agree. This point, 3 negative 4 has nothing to do with the other half of the circle. That's right, it's reflected across the x-axis. So really what I need is I need this when I solve. It's the lower parts. Probably want to do it this whole function, but this is negative 25 minus x squared. And so if you go through, you like your observation is actually the correct one for this particular problem. The only thing that changes is the sign. And so what you get is minus 1/2 25 minus x squared minus 1/2 minus 2x. So in this case, you get x over 25 minus x squared half. So effectively, the only change is the sign. And if I plug in 3, I get 3/4. And again, that's what the slope of that line looks like to me, positive 3/4 of that. But see, here's the problem. When I ask for a slope of the tangent line at a point, I have to do two things. I figure out if I talk about the top of the circle, I've got the bottom, I've got to solve, figure out which one it is, and I've got to take, frankly, a rather nasty derivative. Yeah. There's a way that we can figure all this stuff out without having to solve the line, which is kind of cool. Now, you pay a price, and the price is this. The price is that your formula for a derivative can involve both x and y. So let me do this problem again a couple of ways. Idea behind implicit differentiation is this. Don't try to solve for y explicit. This is not a necessary step. Just assume y is f of x. So assume that you can write it as some function, but don't even bother to try to find it. Just leave it there. Just be content with the fact that maybe I can find y is. Okay, this is true of the circle, right? This equation defines, it's not a function, but it defines two functions. And what did I do in part one of this? I solved for y. Part two, I solved for the different red y down here. Don't even bother. Skip that step and just go straight ahead. Let me go through this problem again under that assumption. I'm gonna write this a couple of ways. So you have x squared so I'm not going to try to solve for y, but I'm assuming that y equals f of x. And what I'm seeking, what I'm trying to find is y prime. I want to find what the derivative is. So what I'm going to do, I'm going to take the derivative of this and the dx. Let's take the derivative of both sides of this equation. Now let's go through it. We'll do the left side first. What's the derivative of x squared? What's the derivative of f of x squared? Okay, good. So this is a blob squared, right? It's the derivative of blob squared. It's 2 blob to the 1/2. But am I done? What do I get to multiply this by? There you go. What's the derivative of the right side of this equation? What's the derivative of 25? Good. And so this allows me to isolate and find it from x. Two f of x at prime base is minus 2x. And f prime of x is equal to, see, I can cancel those twos, minus 2x. Notice. That's exactly what we got. Negative x on top and f of x on the bottom. So I get the same answer that I got when I did this explicitly. This notation is perhaps more handy and quicker. Let's do the same thing over here. Same approach. Take the derivative of this. What's the derivative of x squared? What's the derivative of y squared? Times the derivative towards the side, which is 5. So the derivative of x squared is 2x. Derivative of this is 2y, y prime, 0. And I solve the y prime. And what do I get? I get minus x over y. And notice y and f of x are the same thing. The price you pay here is now you have the derivative in terms of x and y. Right? When you do it explicitly, your derivative is completely in terms of x. The price you pay for implicit is sometimes you have in terms of y. But look how quick this makes this. Here we have 3, 4. Here we have 3 minus 4. And y prime is minus x over y. That's what the formula gave us. Correct? Just shove these points in and see what happens. Up here, minus x over y. Here, minus x over y. How about that? Very good. Everybody agree? Now, this is a implicit differentiation. Now, for those of you that are stubborn, and when I was your age, I was certainly among this, you might think, well, old Jim could have saved us a section, and I could just pound through it and do it explicitly all the time. Let me give you another example. Play. Anybody know what this curve looks like? It's not trivial. When we get when you get to 1080, part of what you do, parametric stuff that will allow you to figure out exactly what this looks like. I could just tell you for now, it's very pretty. It looks like a little bow. Until like this. That's what this looks like. Now, this isn't a function, as you can see, right? Everything over here is kind of cool, right? Working line is no problem, but here you got a series problem. If vertical line passing through. Right? Now, we had this problem with the circle. Remember how we solved for y? X squared plus y squared is 25, so we solved for y. Solve for y here. Actually, I did this for you. But there are actually multiple solutions. One of this is this. Let's suppose that I want the tangent line at point 3. By the way, 3, 3 is a point on this curve. Does anybody know how I can, how could I check? I mean, I just may have made that number. Plug in X and Y, see if it balances. It's like in chemistry. You put in 3 here and 3 here, you get 27, 27 is 54. Plug in 3 here, 6 times 9 is 50. So what does it look like? It looks like it's probably negative if I've drawn this right. That. Well, suppose I wanted to solve this for y, just like I solved for y in the circle. One solution of this is this. There are a number of problems with this. This is correct, but number one, where did I come up with? How many of you know the quadratic formula? Yeah. You know this, right? How many of you know the cubic formula? Nobody teaches this. It doesn't exist. You can do this. That's the first problem. Here's the second problem. Who wants to take the derivative? Nobody. Like nobody wants to take it. Like this is a nested chain rule. This is like, remember when I had the square root and the square root, y'all thought I was being evil. Well, here's an application that actually comes up. Right? Nobody wants to do it. And here's the bigger problem. This is not a function. This is. So this describes a piece of it. Which piece? Is it this? Is it this? Is it this? I don't even know which piece that is describing without checking further. It's another one. Everybody see? Could be this. However, let's find y prime and find the tangent line. Let's do this. X cubed y. Now, you get y prime, which is what we're hunting for. What's the derivative of x cubed? Agreed. What's the derivative of y cubed? Chain rule. By the way, be honest with me. How many of you are a little bit puzzled by the fact that there's a y prime opposite? Yeah, it's a little strange. Why? But I'll tell you why. Let's be even more careful with this. Let's start over. Let's do the chain rule here. What's the derivative of x cubed? It's blob cubed. Agreed? 3x squared times the derivative of what's inside there. Derivative of x, what's inside there is x. What does that turn into? 1. On the other hand, when you take the derivative of this is 3 blob squared times derivative of what's inside. Y. This is one. So people don't even bother writing, it's just 3x squared and go to pass, right? 3y squared, I'm taking derivative with respect to x, 3y squared times derivative y is. Does that make it a little bit clearer why that y prime is there? So just be careful about that. This one is a product rule, right? So I'll do it this way. Derivative of 6x is 6 times y plus 6x times the derivative of y. So let me write this a little bit cleanly. Now, I believe the question was solved by time. This step is always doable. Here's what you do, you kind of divide and conquer. Put all the stuff that has y primes on one side, all the stuff does not have y primes on the other. So we'll see what I'm gonna have, 3x squared minus 6y and 6x y prime minus 3y squared y prime. And this allows me to pull out y primes. Y prime is 3x squared minus 6y over 6x minus 3. And there you get a nice rate. Again, nobody wants to take derivative of this. And even if you could, it would be incomplete because this is only a minuscule piece, this whole curve. This tells it for you everywhere. Let's find that tangent line too. And I want to make a couple other observations, then we'll do some examples. But any questions? So, okay, let's find the tangent line. Use this to find well, here's the deal. All you gotta do is notice, by the way, there's another point on the curve that has x coordinate 3. There's another point on the curve that has y coordinate 3. The 3 specifies only one point. And so if you plug in at 3, this is equal to 27 minus 18. So both x and y plug in 3, so it's 3 times 9 is 27 minus 18, and then I get 18 minus 27. So that's 9 over minus 9, so you make. So given my picture here, this doesn't seem like an unreasonable glance. So the tangent line is y minus 3 minus 1 x minus 3. Or if you like, minus x plus 6. Right here. By the way, here's kind of interesting. Does anybody see a point on the curve that is bound to cause problems, even for our implicit differentiation? That's exactly right, because this curve passes through the origin twice. And so if I ask you, hey, Mr. Curve, what is your tangent line here? Well, from one perspective, it should be horizontal, but maybe from another perspective, it would be vertical, right? What happens when you plug in? If you're just empty headed, plugging 0, 0, you get 0 over 0, right? And again, that means there's more work to be done. When you get into 1080, you'll be able to analyze this a little bit further, but you have, it's not, you don't get like 2/0 indicating that there might be a vertical tangent or a custom. So you actually get 0/0. And that means it's like Wednesday on the Mickey Mouse Club Day, anything. It could be a horizontal tangent, it could be vertical tangent, it could be custom, it could be something else. And we see what it is here, but that's only because kind of the curves. But any other point that was flat tail. Okay, any questions on that? Let's do just kind of practice. Do another one of these. Let's find a y prime. Check this here. See how this shakes out. X prime equal to x squared plus y cubed plus tangent I'm here to tell you it's a mess, but we will persevere. I want to make sure that we get all. I've got it. Okay, so let's think about the chain. Derivative of e to the blob is blob. But I'm not done. I've got to multiply by the derivative of whatever this is. And what's the rule that applies to this? This is a product, right? So let's go through, everybody gets their term taken derivative. This derivative of x, 1, y, plus x times the derivative of y, which is the other side. Derivative of x is 2x. Derivative of 2y cubed is 6y squared y prime. Everybody okay on it? And finally, let's see, what do I get? I get tangent of some mess. What's the derivative of tangent of law? Secant squared, good. And now I've got to multiply by the derivative of what I find inside the parentheses, which is a product rule with a chain. So it's derivative of x times y squared plus x times the derivative of y squared, which is 2y. What a mess. Now, unfortunately, here's the algebra step where I'm going to kind of clean it up a little bit. So if I multiply this through, I get y e to the xy plus x e to the xy y prime. This is 2x plus 6y y prime 6y squared plus we get y squared secant squared xy squared plus 2xy secant squared xy squared and y prime. So this is again a divide and conquer job. On the right side. So I'm underlining all the stuff that has y prime in it. So I'm going to bring this over to the other side. So I'm going to have 6 I'm gonna have 6y squared y prime plus 2xy secant squared xy squared y prime. Got those two accounted for. And then this over the other side minus x e x y y prime. So there's the step on right side. I'm gonna dump this stuff back over the other side without the y prime in it. So I get y e to the x y minus 2x and minus y squared secant squared x squared. All I gotta do is pull y prime out of this other side and divide. 6y squared plus 2xy secant squared xy squared minus x e x y all times y prime. Y x y minus 2x minus y squared secant squared x squared. And finally, in our moment of triumph, we'll divide by this thing over. So it will just be left side that factor. Over 6y squared plus 2xy secant squared y squared minus x. And then okay. So let me take questions. Let's kind of see. Okay, you all want to hear. I need you all to try this one. See if you can work through this. We give you this equation here. So this function y defined implicitly, y to the fourth plus x squared y squared is sine by the way. Let me check here. How do I know that 0, 0 is even on this curve? Notice it balances. If x and y are 0, I get 0 on the left side. Agree? And on the other side, I get sine of 0, which is so. See if you can find the tangent line to this curve that goes through the origin. let me give you kind of a hint, and you're thinking about this too. Of course, you're going to need what the derivative is to find it, right? Because that's a constant tangent. But you don't need the derivative. You don't need a formula for x and y. You only need the derivative at this point. Right? That's all you care about. That might simplify what you're doing. This is still almost so this I agree. Very well. One plus parentheses one plus. Yeah, No, maybe, because. It's exactly sure. Okay, you all were all making good progress. Let me, see if I got an answer. Yeah, but there's an easier way also. Like it. Okay. Question is find ten. Need two items today. I need 2 points as a point out last 4 points. So we've got the point 0, 0 in the story. So the burden on us is to get slope in. Now, I think almost all of you got this with maybe some minor errors on the way. Derivative, y to the fourth is right. The second term, partial product, right? That's something that x squared constant. So let's go 2x y squared, and then it's y squared's turn to have an x derivative taken. So this is 2y y prime. Everybody understand that? Everybody okay? So everybody got the left side. Next step, sine of block. What's derivative of sine of block? Now, the burden is multiply by the derivative of what you find inside. Derivative of x plus y. Derivative of x is 1, and the derivative of y is. Everybody comfortable with this? What's the next thing to do here? You distribute the cosine and you can solve for y prime, right? But in this case, let me ask you, did I ever ask you what y prime is? Do you really care what y prime is? You only need y prime for one itty bitty piece of information, and that is you only care if y prime is 0, 0, right? So plug in the 0, 0 first, right? Now plug. You can do it the other way, but it's more prone to what you were doing, Rich, was perfectly fine. You're more likely to make a little mistake on it. Now just plug this in and see what shakes out, right? Because the order shouldn't matter. What happens when you plug in y equals 0 right here? Gone. Gone. The whole left side is gone. Plug in x and y 0 right here. Cosine 0, which is 1. So what I get is 0 is 1 plus y prime, or y prime is negative 1. So there you go. Y is minus x. There's 2. Now, the reason I did this is because nobody asked me what a general form of y prime is. I only care about it at 0, 0. Right? If I had asked you several points, find the tangent line at this point, that point, the other point, it's probably better if you get the formula. But here, 1 point, Why not make it? Any questions? Okay, here's another one, that I want you guys to start for me. This one's kind of, thing. Um, uh, uh, x squared plus xy is equal to y. Find all points on curve with number one, horizontal tangent. Two, undefined. Slope. And you may ignore for the purposes of this, 0.00. Because that requires slightly deeper analysis. Notice that 0, 0 actually is on the curve. So take a couple of minutes to see if you can kind of figure some of the stuff out. All your white prime stuff on one side, so without white primes on the other. Pull out the white prime. So almost all of you are at this point right here. So let's kind of have to do this. Kind of sort of a benchmark along the trail. We'll see even better. Between the written part, which is big part. So you have x squared. Right, so the ddx is trying to get at the y. So this is 2x. This is derivative of x, which is 1 times y, plus x y prime is 3y squared. Okie dokie, simple. So from here, it's just kind of algebra. You kind of divide and conquer. Squared minus divide this into this with y prime. Everybody comfortable to that point? But now, here's the thing. For one, for the horizontal. What does that mean? That means the y prime must be zero. What does it mean for that to be zero? If I have a fraction numerator over denominator, now I know it's zero. What can you say about the numerator? So what does that mean about the relation? Well, this means. Everybody agree with that? But so what? Y equals minus 2x. That doesn't give me any numbers. Doesn't give me any points. Anybody tell me what's missing? Right, I mean, what did I get after all this work? What I got was some lousy equation. Right, it didn't tell me anything. So I was after all looking for points for the change in minus 4. Okay, so where are you coming up with that? No, actually, it doesn't. That actually, it turns out is one solution, but there's one thing. So you're just looking at that equation by itself. These equations should actually tell you something. This tells you if you have a horizontal tangent, then the y coordinate should be minus 2 times x squared. That's what it's telling you. Do I agree? But there's one thing that we've lost the thread on. This point also has to be on the original curve, right? We use the original curve to get the derivative, but this only gives me an equation. So there's two things going on. Number one, whatever your y coordinate, your point that has a horizontal tangent, you got a y coordinate and an x coordinate. This tells you that the y coordinate is negative 2 times the x coordinate. But you've also got to make sure that it's still on that curve. Right? Well, yeah, we got to get the points first, right? Also, this point must be on the curve. See, we took the original curve, took the derivative of it, and found a condition for it to be a horizontal tangent. Y is equal to minus 2x. We got to make sure that this is on the curve. So how can we do this? Plug it back into the original. So x squared plus xy cubed left y equal minus 2x. Everywhere you see a y, put in a minus 2x. X squared minus 2x squared equals minus 8x cubed. Everybody see where I got it? This equation may look intimidating, because what we get is minus x squared is minus 8x cubed. So I can rewrite this as 8x cubed minus x squared. 0 from x squared is 8x minus 1. So what solutions do I get? What are the solutions to this equation? 1/8 making that 0. 1/8 making that 0 and 0. And you also have to have y equals minus 2x. So if x equals 0, I get the point 0, 0. And if x equals 1/8, I get the point 1/8 minus 1/4. And I said you can ignore 0. But so you're right, in the 0, 0 does come up. But there's this. That's the shortest. Because I know what the x coordinate is, it's 1/8, and the y coordinate should be negative 2 times. And you can check it, right? So let's check it. What happens if you plug in x equals 1/8 and y equals negative 1/4? Then that's 1/64th. And that's going to be minus 1/32. And 164 minus 132 is negative 164, which is negative 1 cubed. So this point is actually on the cube, on the curve. And I guess technically I should make sure that this denominator isn't zero, because it could be zero up here and zero here. But it's not, because 3y squared, so y, that's going to be like 3/16 minus 1/8. So I only get 1 point with the tangent. Well, besides what make up 0, 0, which is. But see if you can find where the tangent is undefined. It's the same sort of approach. See what you come up with there. So Notice, this is always defined unless that bottom is C. So it's undefined. If only, X coordinate is 3 times the square of the Y coordinate, then you get 0 at the bottom, right? Now, again, just like before, let's make sure, what does it take for this to be actually on the curve? square. So you go square like that. So that's where you're. But your attack is good. Now let's do this. Good. Oh, there you go. That's it. You got it. Okay, folks. We got one more thing that I want to do. But let's get this out. So this is the same problem with before. Except now instead of saying, well, the memory is zero, now we're saying, well, if it's undefined, look, it's spoiled. Um, so X is 3 much greater. So this is just something, the equation is telling me something that when, if it's undefined, the X coordinate has to be 3 times the square of the Y coordinate. I need a number, I need some points on here. So put this back in the original. And there's your X squared. Plus it's like 9y4 plus 3y2 y cubed. So let's just 9y4 plus 2y2 0, and we'll pull out a y cubed. Y cubed times 9y plus 2 cubed. So your y is 0, negative 2 months. So what points does this give? So this gives x is 3y squared, so if the y coordinate is 0, then this coordinate is 0, and this is the one I said that would shows up with both the numerator and the denominator 0 there. And y coordinate is minus 2/9. Square that, multiply by 3, get the x coordinate for cells. Check that point is on the curve and find you get the 7. Okay. Any questions? Okay, there's one more thing I want to talk about before it's quiz time, and that is higher derivatives. So when you first learned about derivatives explicitly, you know, you might have something like, okay, take y equals x cubed, right? What's the derivative of x cubed? Y prime is 3x squared. What's y double prime? 6. So you can just keep taking derivatives, right? You can do the same thing with implicit differentiation, but there's a little click. Again, when you take a derivative implicitly, we've seen this, then you get derivatives that involve both x and y. Take another derivative of this, you'll get x, y, and y prime, but you can use that, you can always get these in terms of x, y. So let me give you an example. Find you might practice this on some of the other functions as well. Okay, the first thing here, R is the number, like it might be 25, whatever, like. Okay, so the first thing we're going to have to do, if we're going to have the second derivative, is we've got to go through the first derivative. We've got to get that first. And this is 2x plus 2y, y prime. See, because right side is just. And we can solve for this and get, and we've seen this before earlier. The derivative is negative x divided by the y. Right? Notice, by the way, that it does not depend, this formula does not depend on the radius of the circle. And that makes sense, right? Because really the only thing that should matter is the ratio of the x coordinate to the y coordinate, right? So at this point on the smaller circle, this point on this bigger circle, they should have the same slope of the tangent line. It would look better if I draw it better, but everybody, so it didn't depend on the radius. How do I get the second derivative? You do this just like you would do any derivative. This is a quotient rule, agree? So you get a new fraction. New fraction, the bottom is the old bottom squared, right? Let's just be careful with this. It's bottom times the derivative at the top minus the top, so it's plus x times the derivative at the top. Now, this is correct, but incomplete. Because you've got to know three things now. You have to know what X is, Y is, and Y prime. I would like to just have this depend on X and Y instead of also having Y prime. How can I do that? Well, sort of, because I know what Y prime is. This is equal to minus Y plus X, six of Y. Let me clean this up a little bit. I'm gonna multiply top and bottom by Y. Minus Y squared minus X squared. And now I've got a formula that's better than it was before. Because now there's no Y prime, it's all equals. But I can make it even better. Does anybody see that? Now, I mean, you could write that as two separate fractions, but look at the original equation. So I can replace that numerator with minus R squared. That means basically the concavity depends only on what the radius is, which is a constant, and the y coordinate, right? Notice that if you look at this, this is saying something to you as well. If the y coordinate is positive and the concavity is negative, right? Look at the circle. When the y coordinate is positive, it is frowning, right? So it's concave down. When the y coordinate is negative, then the concavity should be up, should be happy, and the bottom part of the circle smile. And you can continue the process forever. I'll do one more step. Y double prime is minus R squared. Y cubed. So Y triple prime is, in fact, it's this way because up short. Y triple prime is going to be, remember, this is a constant. Minus 3, y to the minus 4, y prime. So up a little bit, just to make it look a little bit presentable. This is 3r squared, y prime, y to the 4th. For y prime again, x of y. So this is going to be minus 3r squared x over y to the 5. I've got a formula depending only on x. Okay. Any questions? I'm gonna give you one more application, which might be a little bit surprising, but this will be a big focus of what we do tomorrow. And then I'll time for your quiz. Well, this is actually easier than probably the last couple of things I've done in a certain sense. But leads to something. Really cool. What's derivative of this? One, no problem there. Derivative of e to the blah. Blah, and in the middle. So. So y prime. Is 1 over e to the y. Great. Very good. Look back to the original equation. Is there another name for e to the y? So if I wanted to write this in a way that would, not confuse my friends quite so much, I could write this as what? 1 over x. If I were to solve this, what would I do? So if x is e to the y, what is y? Let's bring to the log there. It is the inverse of the exponential, which is. We've discovered something actually. Right? Starting with this silly little problem, we got that y prime is 1 over e to the y, but hey, y is. We have discovered that if y is log x, then its derivative 1 over x. This is actually fantastic. What's the derivative of x to the n power? What is the only power of x that is not achievable through this formula? So for example, if I wanted this to be 2, all I'd have to do is take n to be 3. Derivative of x cubed is something times x squared. Derivative of x4 is something times x cubed. If I wanted this to be 1,000,000, I just take that to be 1,000,001. What is the only power that I can't get on that right side by doing this form? Actually, x is the negative. Because if I get a -1 over here, what does that mean in x today? Well, so for you to get a -1 over here, that would be n has to be what? 0. What's the derivative of x to the 0 power? It's actually 0, right? The derivative of 1 is 0. And that's because look, that n drifts down and the 0 makes it go away. Using this formula, it reduces the power of x. The only power of x that you can't get by this formula on the side of the equation is the -1 power. And there it is. Log. We'll talk more about that. Any questions? Okay, so let me give you all your quiz.
Anyway.